All right, so here's chapter 9, problem number 69, where it says a 1 meter long massless rod is pivoted at one end and swings around in a circle on a frictionless table. A block with a hole through the center can slide in and out along the rod. Initially, a small piece of wax holds the block 30 centimeters from the pivot. The block is spun at 50 revolutions per minute. Then the temperature of the rod is slowly increased. When the wax melts, the block slides out to the end of the rod. What is that? Final angular speed. Give your answer in revolutions per minute. So I've drawn a little diagram of our setup that they tell us about. It's a little confusing in what they tell us, so I just drew something to help you visualize it. So we've got this long, they say, massless rod, which is nice. It's massless, so we don't have to worry about the moment of inertia of it. Because if you remember, just real basic, moment of inertia is mr squared. If there's no mass, then we don't have any moment of inertia. So the only moment of inertia that's going to affect the rotation of our system is going to be this block. So we've got our block here, and it starts at 0.3 meters away from the pivot point, from our axis of rotation. And they say that there's this little bit of wax right here that is holding the block in place. And then they say somehow that we increase the temperature of the rod here, this blue rectangle, and it causes the wax to melt, thereby freeing this block. And as it rotates around, it slides all the way to the end of the rod, which is then 1 meter away. Okay, so using that information, they would like to know if we started 0.3 meters away and we then slid out to 1 meter away, what would happen to the final angular speed of our block? So because we have this thing spinning around and it's rotating, we should remember that angular momentum is always conserved. Right, so the angular momentum that we started with must equal the angular momentum that we finish with. Okay, so super quick, that means then that moment of inertia initial times the initial rotational speed has to equal the final moment of inertia times the final omega. All right, so again, we're only dealing with this block. We can treat it as a point mass, so it would be mr squared, right, times omega sub I is equal to mr squared times omega sub f. And because our block doesn't change, the masses, they cancel out. They don't play a part in this equation. Okay? So if we go through now, when we plug everything in, our first r, which is when it's 0.3 meters away, so it's 0.3 squared, and they tell us that it has that initial rotational speed of 50 revolutions per minute. Then the wax is melted and the block slides out to the end of the rod. We find then that its new radius, its new distance from the pivot point, is going to be 1 meter squared times omega sub f. So solving for omega sub f, we find then that it needs to be 4.5 revolutions per minute, which makes sense. All right, if momentum is going to be conserved, the momentum before a change in the moment of inertia needs to be equal to the angular momentum after the change in moment of inertia. So if the moment of inertia went up, that means that the angular speed needs to go down, which it agrees with because it went from 50 to 4.5. So there you go. There is problem number 69 from chapter 9.